the girls' rooms. They're not even listening. You're good. All right, real quickly, and so it's recorded. I have a few people out with Corona, possibly.
In here?
They're not here. But what are you supposed to do if you get a positive test or think you have a positive or anything like that?
You have to email the
Stay away. And then you email the school, right? You know, you're supposed to tell the school? All right, making sure. Reason I'm saying that, so I haven't looked at my email, but I got an email today that basically has the numbers of positive cases. And even though the county's dropped, we were at our high last week, the school was. So it is around. Now, every student I have that has tested positive has sniffles as the worst symptom. So that's a good sign, right? That's a good sign. Sniffles is just, if that's what Corona is, would anybody worry about it? Of course not. So that's a good sign. Vaccines are doing what they're supposed to. People who are sick are having mild cases, et cetera, et cetera. All things good in the world. Is that about where we stopped?
Yeah, we finished that.
We finished that one. I thought we did. Now ready to start. This one, which is another one of these pens. And thank goodness I got this pen mostly working because the earlier class, I wrote this stuff on the wall. And let me tell you, it kind of stunk. I see I didn't erase everything. We'll blame you again for that. That seemed reasonable, right? How come you didn't erase the wall? The worst thing is for anybody who's online, they were trying to watch that through the camera and the camera follows me. I can't make it manual. So I had to stand over there for you to see anything. Before we get going, I need to start up the calculator because we're going to show how to calculate quite a few of these. At first, we're going to do it with introduce how to apply the use of a graphing calculator, which speeds up the process and gets you the exact answer. And then we're going to show you some of the techniques we can use to approximate the answer, which is still just as good. Approximation is accurate and it is reliable, but obviously not nearly as good as exact. But it is going to be on a graphing calculator to really do this. So if you have one, break it out of its antique parlor trick site, and we'll be using that in the class. And those of you who don't have a fancy graphing calculator, if you just have a standard one, we will be solving it that with the standard calculator as well. So you're going to see both. Okay, so on a problem like this, and it just has a basic setup, I've given you the starting conditions for HI, and we just want to let it go to equilibrium. And we're told what the HI concentration is at equilibrium, and we're going to just use those two numbers to calculate the Kc. Piece of cake, right? So how we're going to do this, I got to turn on the marker because it doesn't work quite the same anymore. How we're going to do this is we actually create that ice table. Ooh. The pen is ever so slightly different. I got the screen size wrong. I got write a little bit bigger with this little tablet. All right, that'll work. All right, and an ice table is so named because here on the side, we're going to write the letters I, C, and E. And all we know on this one is on an ice table, we're going to put the concentration or the pressure, atmospheres. Since I have moles and liters, we're going to do concentration. And the concentration here is going to be essentially 0.2 divided by 2 liters, or 0.1 molar. It doesn't tell us anything at all about the H or the iodine. In that case, you always assume there is none. Now, on the previous one, the one we did last class, I gave you enough that we had to calculate a Q to figure out which direction it is. This one we can know it's going to forward because I have zeros. Can't go away from zeros, so the only thing you can possibly do is make more products. This is going to go down by twice that amount because of the 2 in front of that HI. Now, quick little side thing right there on that direction thing. A trick problem that the book does, I'm going to put it way over here, is they do this weird thing where we got A plus B, doesn't matter what they are, turning into Z and D. And you know how I just had this nice little rule that if you have zeros, it goes towards the zeros? Well, let's say we have 1 and 0 and 1 and 0 and the same K. Which direction would it go? Why?
Because the zero is in between 2 1s.
Both sides have a 0 though. You're right, if only one side has a 0. But what's going to happen if there's zeros on both sides? The trick is, all right, I asked the question, is it going to go forward or backwards? That's really not the only choices. There is nowhere, and which is really what's going to happen. It can't go forward because there is a 0 here. And it can't go backwards because there is a 0 over there, which I can't get to there. Weird mental sections. But because of those zeros, this one will do nothing at all. It's not going to go forward, not going to go backwards. Until you add either that B or D, this reaction stays non-motional. I know that's a weird trick the book likes to throw at you on some of these to really understand what direction something's going. But if there are zeros, you typically never have to calculate Q. The zeros tell you which direction the reaction's going. In this case, it told us forward because you can't go away from a 0. All right, now that we have that, we could actually figure out what our equilibrium values are. This is going to be 0.1 minus 2x. This would just be x, and this is x. We get the equilibrium, or the E rho, just by adding the I and the C. Now, typically when I finish the Q, or the ICE table, I actually go ahead and immediately figure out what my Q will be, and that is just products minus reactants, or products over reactants. That'll be squared because of that 2. All right, now here's where this gets interesting. There are going to be times I ask you to calculate a K, like I do here. There might be times I ask you to calculate the X in this problem. And there's going to be a few ways to get the X. In this case, I am going to need the X, and I'm going to get it from this 0.078. Because see how this says that's the HI concentration at equilibrium? Well, I also know that that's equal to the 0.1 minus 2x. HI at equilibrium equals 0.078. I can fix that. That looks terrible. How do I get the eraser easily in mouse mode? Yes?
Where'd you get the 0.1 again?
0.2 divided by 2. So 0.0, the top of the board, or top of my tablet. Man, that's a 7/8. Apparently I can't write 1s or 7s today. 0.1 minus 2x. So I can figure out what x is because I could just start with that 0.078. Subtract the 0.1 to move it over. And then divide by -2. And I get an x of 0.011. Now, sometimes that's what it's going to want. It might have given us the HI and asked you to calculate the equilibrium amount of the hydrogen or the iodine, and it would be just 0.011 in this case. But this one wants us to calculate the actual Kc. So we want the numerical values of everything here, and we're going to plug those into this Q equation. So in this case, the Q is the H, which is 0.011, and the I, which is another 0.011, all over the 0.078 from that squared. Point 0.011 times 0.011 divided by 0.078 squared gives us a Q of 0.020. And since we used all equilibrium values, that is also the K. So our K is 0.020 with no units. Not too bad, right? All right, we're going to make it slightly more challenging on the next one. But we're doing the exact same thing every single time. We're going to create a nice table as best we can. We're going to create that Q as best we can. And both of those two things are done to organize our thoughts more than anything. Sometimes we won't actually do the entire table or need the entire table, but we're going to always set it up. Try to use it. Sweet, huh? You guys seem awfully tired today. Partying too much overnight? Binge drinking again? You probably shouldn't do that on a Wednesday. Just saying.
I applaud people that can take classes like this and still go out and party all the time. Like,
Well, the weird thing is, this is not the time you're tired when you party all day. Because if you party all night, this is about when you start waking up. This is your 8 a.m. You're starting to feel good. So this is a typical, you did high school type day. You were up at 7, 8, whatever. You did your morning thing. You just had lunch or you didn't. Either way, you're kind of tired. It's the middle of the day. What's the worst can happen though? You fall asleep in class and we make fun of you. Tie your shoelaces together. You know, I've seen that on like funny home videos on YouTube, but I think if you really were to do that to a student, you'd get in trouble nowadays, wouldn't you? Isn't that assault? Yeah, something like that. Ice table. Now this is a weird one because I gave you a bunch of numbers. I gave you a bunch of numbers up here, but it actually does say they're at equilibrium. So we are going to put these in as the E row, but we're not putting in 0.26. Anybody know why? It's because of the moles. Our ice table always gets and only ever gets molarities or atmospheres. That's the only thing that can ever be in here. All right, so I'm going to take, for instance, to get the CO concentration, I am going to take that 0.26. And I'm going to divide it by the volume of the flask we're in, which is 0.32 liters. So my CO at equilibrium is 0.81 moles. 81 molar. To get the H2, we're going to do the 0.091 divided by the 0.32. And so the H3 is 0.28. It's weird. And none. Technically, as I'm getting used to this, I can write in the dead center of this tablet, which seems to always work a little bit better. I just have to kind of like move, picking up the mouse. And my last number is 0.041 for the CH4. I'm taking that divided by 0.32. And I get 0.13. And you look up there, it wants to know what the H2O is at equilibrium. We are technically looking for that. That's our variable. All right, so now I'm gonna do my little Q equation. So I got my carbon monoxide and the hydrogen. The hydrogen will be cubed. And I have the methane and water. And I have these equilibrium values. I have the K. They're all going to get plugged in at the same time. So 0.26 is what we get if we were to take the 0.81, multiply it by the 28 cubed, and divide it by 0.13 and whatever X is. Fun, huh? Solving for an X on the bottom of a fraction. Remember in college algebra, they told you you would use that stuff someday? Today is that day. I'm going to start with everything on the left, so the 0.26. I'll multiply by this to move it over, so times 0.13. I will divide by the thing on top, the 0.81, and the other thing on top, which is 0.28 cubed. And I get this wonderful value. Is that X? No, it's 1 over X. So to get my X, or the concentration of H3O, I'll invert this. And I get that the H2O should have a concentration about 0.53. So X equals 0.53. And in this case, that is also equal to the high H2O concentration. So far, so good, right? Just been basic algebra. Might be a bit of a challenge to get to the basic algebra, but we're doing ice tables to organize our thoughts and then plugging stuff into a equation we create and then solving that equation. Now we're going to start moving into a little bit more complex questions I can ask with this type of thing. Now, this one, while it looks like it's all starting out the same idea, where it gets to be a little bit trickier. See down here, it says, what's the composition of the equilibrium mixture? And the other thing that makes it challenging, if you look through all those words, I don't say anything at all about any concentrations at equilibrium. So I'm telling you nothing directly about the final states, yet I'm asking you everything about the final states. Those typically are our more involved calculations. But we're still going to start out the exact same way. And what's the first thing we do on these? An ice table. And did the same type of thing. I gave you moles and I told you the volume. So 0.25 moles of CO and a 0.125 liter flask is going to give me a 2 molar solution. And that's for the CO and the water. And if I don't say anything about the products, how much do we assume there was? 0. All right, so which way is this reaction going? Forward. Got to go towards the zeros. So these two will be going up. These two will be going down. And at equilibrium, we have 2 minus X and 2 minus X and X and X. Ice table is complete. Now we'll create our Q for this equation, which is kind of nice, except I'm running out of board. CO2 and H2 all over CO and H2O. I'm going to plug in my equilibrium values from the bottom of the ice table along with the K and get a new equation that I need to solve. On 0.56, the K, is equal to our CO, which is the X, and the H2, which is X, all over 2 minus X and 2 minus X. We need to solve for X. Now, it turns out, you might remember a nice little trick you could do from college algebra that makes this one really easy to solve. Anybody know something we could do to that fraction to simplify it? See, it's a duplicate, it'd be x squared and then 2 minus x squared. Well, I can,
You mean FOIL it or?
I'm gonna FOIL it. FOIL would make it more complex, but technically, square root of 1.56 would therefore be equal to just x over 2 minus x. And isn't that a heck of a lot easier to solve? Yeah. Now we're gonna start distributing. I'm not gonna figure out what the square root of 1.56 is, but 1.56 is gonna be multiplied by that 2 minus x, and that's gonna be equal to x. And now I can solve this. Square root of 1.56. Anybody know what that is off the top of their head?
2.
2? Not even close. Actually, it's close, not close enough. 1.56 is 1.24, 1.25. What's 1.25 times 2? What's $1.25 times 2? 2.5. So I got 2.5 minus 1.25x equals x, or 2.5 equals 2.25x, or x is 2.5 over 2.25. We can solve this solely. We can solve this totally with algebra. 2.5 divided by 2.25, we get an x of 1.11. And with that, we can now safely say our two products, the CO2 and the H2, since their concentrations would be equal to X, are actually equal to 1.11 molar. We could also say carbon monoxide and the H2O, which were equal to 2 minus X. I can just do that math. 2 minus 1.1 is 0.89 molar. And we got our final conditions. All with basic algebra. I probably should say basic, right? All with college algebra. Because you did do that in college algebra, right? Yeah. Even though you probably also did it, what, 8th grade, 7th grade? We'll call it college algebra.
Never had it.
Huh?
Never had it.
You never had college algebra? How are you in this class?
I tested out of it.
You tested out of college algebra?
Yeah.
And you're as bad at this as you are?
Yeah.
It's weird. So it's harsh. When I was in college, just a weird thing, since I declared myself, I had declared as a psychology and I think biology major. I forget what science I said, but the science major aspect. Regardless of what test I took in math, I was starting in calculus. Because that was part of so you know how you have to test out of college algebra? Mine, the program I signed up for me, got me out of college algebra when I started writing calculus. That's how they did that. We've talked about that here. If you declared yourself as, chemistry focus or physics focus or engineering focus, make you start in Chem 1 rather than in intro? As in, no, you don't get a choice. You're just going right into Chem 1. But that never actually gained much traction. We should do that, though, don't you think? Skip intro?
I thought that would be easy.
But it depends on them.
Depends on the person.
Yeah, it does. And chemistry, someone wanting to go into chemistry probably is interested enough they could do that. So certain fields, yes. I don't know if it's going to be across the board. All right, let's make this a little bit harder. Something that won't square root out. All right, so I got phosgene, which I put on this slide as a chemical warfare agent, which we use in chem labs. But it's all on how you choose to say things. Did you know that another warfare agent that's now outlawed is just chlorine? You can't use chlorine in a war because that's now a weapon of mass destruction. Yet some of you use it in your swimming pools.
HMO is also.
Yes, well, HMO can be. All right, decomposes following reaction. Calcium carbonate turns into carbon dioxide and chlorine, which is the problem we have using it in our chemistry labs, which is why I don't use it. All right, but we want to calculate the final concentrations given just the K and the initial amounts of COCl2. We're doing very much like we did on the previous slide. But this problem is going to be slightly harder when we go to reduce that fraction. So same thing, type of thing as before, we're setting up an ice table. In this case, we have 5 moles divided by 10 liters, or 5 molar. How much do we think we should assume for the CO?
0.
And 0 here. So which direction the reaction going? Forward. So at equilibrium, we'd expect this to be 0.5 minus X. This is X, and this is X. Now I have a potential Q. Not a potential Q. I have a Q that's going to have our carbon monoxide and the chlorine up here on top, and on bottom is the phosgene, COCl2. Now we know at equilibrium we got have our K, which is the 8.3 times 10 to the negative 4, and it's going to be X and X all over 0.5 minus X. Not so easy to reduce, is it? Technically, we can work that out and it would be a quadratic equation. Not going to do that quite yet. Because before we do any math with this, we know this is going to be a challenging one because we can't just cancel stuff out. We're going to have to solve a crazy equation. But there is something we can do, and that is estimate the size of the X. And how we're going to do that is we're going to look here at the K and see that that K is very, very small. And do you remember if I had a small K, does that mean it favors reactants or does it favor products? And even think about this fraction. If I want this fraction to be small, what numbers would I like to be larger, the bottom or the top? The bottom, right? All right. A small K does mean that we would expect this to be very small. We're not expecting to go very small forward. We're not expecting to go very far forward. So in that case, something we are able to do is a weird assumption. It's going to seem weird at first. I'm going to explain what we're doing here in just a second. If I can change my pen color. I can't change my pen color. There we go. So, and we're going to go back to the red in just a second, but we're going to do something weird with this equation. I'm going to pretend like whatever the X is, it's so small that that 0.5 on the bottom never really changes much. And if it doesn't really change much, it stays at 0.5. Now, the reason I did that, isn't that equation much easier to solve? Oh yeah, I just take the 8.3 times 10 to the negative 4th, multiply it by 0.5, and then take the square root of it. Which is what I'm gonna do real quick. 8.3 times 10 to the negative 4th times that 0.5 that was on the bottom. And then we're gonna take the square root of that. And we get a very small 0.020. X equals 0.020. Now, I gotta ask, is that a small X? Yeah. Yes.
I don't understand how you could just like get rid of that X.
Well, what I'm doing is introducing some error. Now, I know it's some error because if the X is 0.02, this should have actually been 0.48. But my question isn't, did I do it right? It's, am I allowed to add that much error to the answer?
So it doesn't matter if it's.
That's exactly right, if it's not much error. Now, how we're gonna check this, we approximated this 0.5. So all I'm gonna do is I'm gonna take that 0.02 we just calculated, I'm gonna compare it to that 0.5. I wanna know what percent of the 0.5 that 0.02 is. So I just do a percent calculation. And if I do that, I see this is really small. 0.2 divided by 0.5 is about a 4% difference. And that's on, I'm not really need to do this super accurate. I just see that 4%. Now, what that tells the mathematicians, by taking that shortcut, you've added as much as maybe a 4% error. Anybody okay with a 4% error? It really probably is one decimal place wrong. So because of that, we can safely make this. We can actually make that assumption and do it. Perfectly legitimate. And that does mean that we can use this x of 0.02 and give ourselves an answer that says the COCl2 is indeed 0.48 molar, because that's 0.5 minus the 0.02. And our carbon monoxide and Cl2 would both be equal to the x, which is 0.020 molar. That is perfectly acceptable. Now, the weird thing is we made this assumption. It might not be exactly what I have on the answer key for a practice test, because it turns out on the actual practice test and the real test, I solved that exactly. But that's okay, we can solve it exactly. I'm gonna show you how to do this. So you're familiar with how to actually solve it when needed to, and we're gonna see how big of an error this created. So on this one, to actually solve it, 8.3 times 10 to the negative fourth, and I bring the 0.5 minus x over here. 0.5 times 8.3 is 4.15. That'd be half of that, right?
Yeah.
Times 10 to the negative fourth minus 8.3 times 10 to the negative fourth x equals x squared. And I actually want a polynomial. So 0 equals x squared plus 8.3 times 10 to the minus fourth x minus 4.15 times 10 to the negative fourth. And now I have an a of 1, a b of the 8.3, and a c there. And remember this equation, negative b plus or minus b squared minus 4ac all over 2a. We could use those to solve for the root. Well, both roots in this case. All right, I'm going to actually solve it a slightly different way. And mainly I'm going to solve it a slightly different way is because I have a graphing calculator. And theoretically, somewhere in one of these apps or programs, and I don't know where, the quadratic equation is actually in there, and you can enter A, B, and C, and it will solve for a quadratic. But I don't want to teach that, because that only really works in this one case. If I use the graphing capability, I can solve it always. You don't like that? Did you not know the quadratic?
I didn't know that.
You didn't know the quadratic equation is built in there?
No,
That really, yeah, it really irritates me, to be
I
honest.
can't even work my graph on my
I use it for the integration.
calculator.
It is in there. I have no idea where, because I never used it. All right, let me show you how to solve a quadratic equation the really super lazy way. Now, the neat thing is, you know how a quadratic equation like this, there are two x's that will make that correct. And I know there's two x's because it has an x squared. So there's two different x's that actually give you a value of 0. Only one of them is really going to work. And we're going to search for the one that will work. And I'm going to show you how we do that. So I'm going to enter this equation, the one where we took the q and then moved down and plugged stuff in. I'm going to enter it into the graph. And so none of this other stuff was necessary. So I just do x times x. Now, the next part, I'm not doing the over. I'm not turning this into a fraction. It has a little bit to do with how the 83 does this. It will sometimes mess up. So what I do to make sure that happens so it doesn't mess up, I put the 0.5 minus x where it looks like it's on that same line. I do the inverse to show it's really on the bottom. All right, so those three things, that's this part of the equation. And since to solve it, I need it all equal to 0. I'm going to move the 8.3 to the left. So now I just minus 8.3 times 10 to the negative fourth. And that's this entire thing now in the computer. And I just hit graph and I'll get something like that. Sometimes your scale's auto set and you get something decent, sometimes not. It kind of worked out all right here. All right, now, technically, this does cross 0 twice. If you look at it, is crossing 0 at a negative value and crossing 0 at a positive value. Would a negative value ever make sense here? No, because that does imply there's negative amounts at equilibrium. But math says negative works. What we want to do is we want to find the only value that's positive that actually works. All right, and we're going to use the chart to figure out what our potential values are. We know at the smallest, x must be 0. Because that's where it started out. So x, the minimum is 0. What's the largest going to be? 0.5. Because if it goes above 0.5, this becomes negative. And we can't have that. So what I'm going to do with those two things in mind, I'm going to come back to my calculator and see this calc. Second function, calculate where it's a 0. And I know it's the 0 I'm looking for is between 0, that's the left bound, and the right bound will be that 0.5. And then I go back and tell it to start guessing at 0. And it gets 0.01996, which was that round to? 0.020. So the graphing calculator ended up giving us the exact same value. Not too bad, right? All right, now, which is easier? That's a tough call. Some of you with the graphing calculator will get to this and find it much easier to figure out how to put that in the calculator and solve it directly. Some of you are going to need to try these approximations. Now we're going to do one where the approximation appears to work, but doesn't. All right, we'll see what that means. Now, only thing I did on this one, if you see this entire question up here, I left the question exactly the same, just change the initial starting amounts. We were starting with 5 moles, now we're starting with 0.5. So very similar problem, just a different starting thing. So this is going to have the exact same look as the one we just had on the ice table. Just going to have a different starting ingredient. Got to tell you, this morning this was a little bit easier because since I wrote it on the wall, I just erased that first initial value. So 0.1 divided by 10. 0.01. We're still saying 0 here and 0 here, so we're saying goes forward. So the ice table, previous problem to this thing, the only thing that's changed is the 0.01. On the previous page, it was 0.5, now it's 0.01. The Q will be the exact same. It's going to have that carbon monoxide. Cl2 all over COCl2. We're going to plug stuff in now because at equilibrium, we know this 8.3 times 10 to the negative fourth equals x over x all over 0.01 minus x. Now, doesn't that look exactly like the previous problem? Except for that 0.01? Yeah, so don't you want to try the same assumption technique? Yeah, that makes sense. So I'd love it if I could take that 8.3 times 10 to the negative fourth and just change that 0.01 at the bottom from 0.01 minus x to just 0.01. And it worked before, so we're giving it the same try here because we still are expecting that x to be very small. Hopefully it's small enough that the 0.01 is still 0.01 or close to it. let's see what we get here. 8.3 times 10 to the -4th times 0.01. And then we're going to take the square root of that. And we get 0.0029. All right, is the x still small? Yes. Is it insignificant compared to the 0.01? We're going to do the same type of check. I'm going to take that value and divide it roughly by that 0.01 to see what kind of percent it is. So what the percent error is potentially. And this isn't going to be so good. Divide that by 0.01, multiply by 100, we have 29% potential error. Anybody okay with losing 29% on this test? Because that reason and that reason alone, we can't do these steps. We have to do it with the quadratic or the graphing calculator. Now, for the quadratic on this one actually gets reduced a heck of a lot easier because the 8.3 times 10 to the -4th times 0.01 minus x equals just x squared. This distributes a heck of a lot easier. 8.3 times 10 to the -6th minus 8.3 times 10 to the -4th equals x squared. We can get our a, b, and c that much quicker for the quadratic equation. But I'm gonna still do with the graphing calculator to have another recording of me doing this. And the nice thing is now that previous problem is still in here. I really just need to change that 0.5 to 0.01. So 0, go to insert 1, enter, graph. Almost looks like the same line, doesn't it? Did I do that too fast?
I just didn't know you could do that either.
Yeah, I didn't know you could
I've
insert
been
it. I've been
erasing
like
the whole
deleting.
thing every time I mess up.
Gotta work on your calculator skills, don't you? You know what's so funny? I didn't do this way. I actually used my HP that I used when I was in your shoes to solve this. And I didn't show it on the screen because my HP uses what they call reverse Polish notation. Anybody ever heard of that? Of course not. Reverse Polish notation, if you want to do 9 times 9 in the calculator, I would hit 9, enter 9 times. Of course, right? Isn't that weird? All right, I learned how to do this because a few students started to use this technique. And it was on the 84s. But I found that most people still had 83s when I was first doing this. I had to make it work for the 83s. But it works pretty well because we got a graph here and we're going to do the same thing we did before. We're going to calculate where that is 0. And again, what's the smallest, in this case, what's the smallest amount the x could be, you think? 0. What's the largest it could be? Because that otherwise it makes it negative. And then we'll start guessing at 0 and we get an x of 0.0025. Now, before I move on this, if you look at the x we approximate, 0.0029, on a multiple choice test, wouldn't that have been close enough for you to get it right? Yeah, the approximation would got you close. Somewhere around the 20% error mark, math really actually screws this all up. So when it's a 20% error or so, you are likely going to be close to the actual real answer. Even a 30% error, it can be drastically wrong. So it typically gets to be a little bit more obvious when it's wrong. I mean, I have one of these that if you do it wrong, the x comes out to be 50 or like -2. It's like neither one would even work on your ICE table. So a lot of the times when this approximation fails, it's really obvious it fails. But this was just a coincidence, they came out really close together. But that does give us the ability to say that the COCl2, it's a 0.01 minus 0.0025, 0.0075. And the CO and the Cl2 would both be equal to 0.0025. Trust me, that is a 2. Yes.
So, like graphing it, how do you determine what's like the left bound and the right bound and stuff?
On the actual graph, I don't bother. If I get something that's visible on the graph, that's good. But I don't, on the 83, I never do. When I actually graph on the 83, I typically have the axes and that's it. And it's mainly because the scale is set up wherever it was before. And I never bother to reset that scale. So it's never actually giving me anything useful until I do that calc and find the 0. Now, if you have an 84, there is a way to do this with the intersect. And all you do there is for your Y2, you just set that 0. So you're graphing 2 lines. And mine, that's the red and the green. And now if we just do intersect, first curve, second curve, guess, and it tells me where they intersect with each other. And that kind of works on the 83, but it also sometimes goes crazy. 84 is actually superior on the graphing capabilities. I know there's 84, there's 84 CE, there's 84 SE. They're all over the place on how good they are. The CE is handling it a heck of a lot better. Those of you out with the graphing calculator, you got to do the quadratic equation. All right, mainly because of that. If I actually required the graphing calculator, you would see a bunch of these problems like this on the practice test, on the real test and the practice test. I'm not requiring that. I don't guarantee it. So I actually did set it up so while there is likely to be one where you need the quadratic equation to fully solve it, that's not common. There's only ever going to be one that is quite this hard. All the others on the test and even the practice test are some like this where we can make certain approximations or shortcuts. Now, the reason you need the graphing calculator is these do get a heck of a lot harder. And this is one I can't even solve with a quadratic equation. And we're going to see why when we put it together. But you notice here, the only thing it asks is what direction the equilibrium going. So it's not asking us to solve anything. It just wants to know what the change is, what the C row is. But we are going to set it up the exact same way. So another ice table. And to be honest, what makes this tricky is that 2 in front of the H2S and the 4 that's in front of the H2. All right, but since we're just going to this change row, we won't be actually solving this table totally. All right, so how do I get the I here? I got 1 mole. Am I going to put the 1 mole down for the CH4? Because I want molarity. 1 divided by 0.25, which is the concentration, would say this is 4 molar. The H2S, I didn't do these in order, is 8 molar. The CS2 is 8 molar. No, it's 4 molar. What was that?
The concentration, is it 250 or 2.5?
2.25, because it's moles divided by liters.
Oh, okay, I'm talking about, oh, never mind. I understand.
What?
No, because I thought the milliliters was 2.5.
Oh, yeah, I got you. Yeah, it's just 250 milliliters. Yeah, that would make it a lot different numbers if it's 2.5. All right. Can we tell easily which direction this is going? No, I have no zeros. All right, so I definitely need to actually go ahead and do the Q table. And that's where this one gets to be an ugly pain in the butt, because right here, the H2 will be to the 4th power. And when I was writing this earlier, I actually was thinking, what the heck was I doing? Because we're finding out what the Q actually is, and I wrote this down. 4, and then 8 to the 4th, which I'm starting to calculate in my head. I'm like, why did I do that? But then when I wrote this down, it actually turned out it wasn't so bad, because the 4's cancel, 8 squared will cancel 2 of the 8 squareds there. So this is just 64. And I was able to do it in my head. We good with that? Yeah. All right. So is this going forward or backwards? Why is it going forwards?
Positive number.
That's clever. It's wrong though. Compare your Q to your K. Which is bigger? Your Q is 64, K is 0.36. You have Q larger than K. Back that up to what this fraction means. That's saying this fraction is too large, which tells you the numbers on top are too big. So what do I need to do with the direction of the reaction to get the numbers on top to be smaller? Go backwards. Now that's all this question asked, but we could actually go ahead and complete the ICE table now, because this is going to go up by X. This is going to go up by 2X. This is going to go down by X. This is going to go down by 4X. And at equilibrium, we'd have 4 plus X, 8 plus 2X, 4 minus X, 8 minus 4X. Now, we don't need to complete the table to answer backwards here. I really did complete the table for practice. Now, this is one I would not be asking you to solve for X directly. And that's mainly because I'm gonna do this in different ink, because I just need to write it down so you guys can see what it looks like and how crazy it looks. But we have 0.036, which is our K, would be equal to 4 minus X and 8 minus 4X to the 4th. I'll lower 4 plus X and 8 plus 2X squared. Now, to be quite honest, even in your algebra classes you're taking, if you could properly FOIL all those and get that to a nice little one-line equation, that would be pretty darn impressive. But it would have an X to the 5th term, an X to the 4th term, an X to the 3rd term, and X squared. That is a 6-degree polynomial. Crosses 0 6 times. Very complex. Now, the neat thing is, I actually can solve this on the graphing calculator. That's why we, in the real world, you would definitely do this one on the graphing calculator. This I have to clear up though, because we entered the exact same way. 4 minus X, 8 minus 4X, and then I cube, well, 4th power. And then on the bottom will be 4 plus X. And I want to show it's on the bottom with that negative. And then 8 plus 2X raised to the -2. Wow, right? And then minus 0.036. And it does graph. Technically crosses 0 3 times visible on the graph. There's 2 other times somewhere. But what are my potential values of X? What's the smallest X is probably going to be? 0, which would show it's not going any far. And the negative ones tell me the X could be larger than 4 here. It could be larger than 2 on this one. Because if it's larger than 2, this term becomes negative. So I am going to do the same type of thing where I just calculate the 0. And I know it's somewhere between 0 and 2. That's the one I'm looking for. I get an x of 1.55. So the graphing calculator does work. It will tell me exactly, it doesn't care how complex the equation is. Ironically, my Hewlett-Packard from 1993 did it too. So this is nothing outstandingly impressive for a calculator. It is technically a big, huge spreadsheet where a bunch of calculations are done really rapidly. Fun, huh? Trivial. All right, to be honest, on a question like this, rather than you ever having to try to get that Q, I would do something like this. So look at what B pops up on this next slide. If the CH4 concentration equals 5.56, what is the equilibrium concentration? Now, the reason that comes in handy, that was saying that 5.56 is equal to 4 plus X. So it's telling me what the X is a different way. And that's the only way I do a problem like this. Yes, I believe you can set up the ice table and I believe you can get the Q. I even believe you could successfully get the direction of that even on something as complex as this equation. But I'm not going to ask you to calculate the equilibrium amount on a very complex problem. I'll do something like that, tell you what the equilibrium amount is on one species and you solve it on your own. Even though it was pretty simple to do on the graphing calculator, wasn't it? Kinda. That does take practice to get it in there. All right, we don't need to do that. All right, so our steps have always been the same thing. There's two things we're doing at first, involving it's these three things. But we have our preliminary setup. You have your balanced equation, and from that you can generate your Q always. And you're going to have an ice table or a reaction table where the units are molarity for concentration, atmospheres if you're dealing with pressures. And you'll have to convert one to the other in some cases, but for the most part, we're going to do all of ours in molarity. Once you have that, you would at that preliminary setup, you're going to have the I part of your ice table, and you have your Q. That second step, this thing over here is, well, that's really weird. There's the mouse. Okay, the second part over here, like you can't even see that. The working on the reaction table, that's completing the reaction table. So I've actually done the two top things pretty much simultaneously, or if I back up. I've done those two things almost simultaneously all the time. Sometimes I've completed the entire ice table before I create the Q. Sometimes I just got it mostly complete and then I create the Q. But I could have done any of those in slightly different order, but those two things are always going to happen. Create your ice table as complete as you can and complete the Q from that balanced equation. Once you have those, now we're looking at how does it want us to solve the rest of it. Sometimes you're going to figure out all the reaction conditions because you have to derive the X using the quadratic equation or something like that. Sometimes I give you the equilibrium amounts of one of the species and you derive the X from that. So there's a couple different ways we have you get the X, but the equilibrium is the nice thing. You're actually looking at the equilibrium amount all the time. And if you make an assumption, your assumption can only create about a 5% error. And you do check it. If it's more than 5%, you have to go back and do it the hard, difficult math way. Woohoo! Hard, difficult math. Yeah. It's not that hard. It's college algebra. And you're so good, you got to skip it. How many of you skipped college algebra? Just you? Does that mean all the rest of you had to take college algebra? Do you suddenly feel like a loser or he Poindexter?
I didn't know we could skip it.
Yeah.
Yeah, there's a test. It's not very well mentioned.
Yeah, my high school guidance counselor didn't let me.
Didn't let you?
What?
Yeah, she said I
You have to
needed,
pay for the test, like, I don't know.
yeah, I don't know.
Wow. And you knew about the test, but wouldn't let you take it.
Was it the club exam?
Yeah.
It can be, isn't there another test that's not reclipped?
It's like-
PERT, you use PERT.
The PERT, yeah.
PERT?
The PERT lets you skip college algebra.
Oh,
I was
no.
never told
No,
about
no,
that.
no.
What was your
It
score?
lets you skip
Perfect.
math for
Oh.
college readiness.
Which is what?
I think it was like
200.
Oh,
okay,
okay.
Okay, cool.
I can't remember.
Okay.
Oh, well, like to skip it, you need at least, I think, over
think it's one, around 110.
Like, you don't have to continue.
I don't know of many people who have taken a decent algebra in high school that also took that test that didn't pass with a high enough score.
Yeah, like if you know what you're doing in algebra, you can pass that test. No
Yeah,
problem.
you need to be more like you took that recently in algebra and then took 5 years and lived your real world life, because obviously you only need algebra to do laundry. And then take
Yeah, I
it.
wanna try.
So if you're rusty at all, that test is hard.
You-
Fun, huh? All right. Next thing we're going to introduce is this wonderful thing called Le Chatelier's principle. Now, Le Chatelier's principle, actually, I'm going to skip a few slides and just go to a nice little graph that kind of summarizes what we're doing here. All right. So my graph here, we have a very simple reaction. And if you notice here that before whatever this thing that says time, at a certain time over here, we're at equilibrium. The concentrations are fixed. Now, it means the same thing as before. Reaction still going forward and backwards. It's just that the forward reaction is at the same speed as the backwards reaction. So these concentrations don't change. And Le Chatelier was studying, well, what would happen if I take this equilibrium system and dump a bunch of one of those components, disturb the equilibrium? And that's what it's showing. We just dumped in a bunch of chlorine. Well, not a bunch, but enough. I'll go here to my slide and we added a bunch. All right, I just added something to the reactant side. What do you think is going to happen to the direction of the reaction? It's going to go away from what we added. And that means over time, the concentration of both these would drop and this would go up. And that's what they're showing here. So the chlorine was added and we do see the chlorine start dropping back off. We also see the PCl3 dropping off because that's a reactant. And we see the PCl5 going up because that's a product. But we almost can set up an ice table very much like we did on the previous things. So what I mean by that, let's say we have some equilibrium amounts and we know exactly how much chlorine we add. Well, that gives us a new starting thing. We just add these together and we'd know the negative simply because the stuff we added is going to drop in amount. And everything on that side of the equation would drop and everything on the other side would go up. We actually could do a calculation and figure out what it changes to. We don't really do a lot of math here. What we mostly do with Le Chatelier's principle is talk about what it means is happening to the system. So it really is kind of a definition. Le Chatelier is saying you have a system at equilibrium and you're going to disrupt the system. You're going to stress it. Now, the reason it's left as stress is because I just show you what happens when we add more of a reagent. We're also going to look at situations where adding gas pressure changes it. Adding heat will change it. There are different things that we can do to cause stress, and the stress will sometimes make the reaction go forward or sometimes go backwards. Sweet, huh? All right, so we have that wonderful page, and I have the math thing. We're not doing math with it. There are some math problems in the book where it has you do a nice little table like that. We don't do those in class or on the test, even though they're same type of thing that we were doing. But what we are going to do is weird things like this. All right, so I have an equation, hydrogen sulfide and oxygen making sulfur and water. Sounds like a fun equation, right? Let's make something that smells like rotten eggs from something that smells like rotten eggs. Sweet, huh? And then see if you can tell the difference. All right, but I have these two wonderful things, and I'm going to say it's at equilibrium. And then I want to know what happens to the concentration of the first case. What happens to the concentration of H2O if I add a bunch of oxygen? Now, what I do on these, especially if I have space, is I take my balanced equation. So I'm going to look at A right now. H2S plus O2 giving me 2 sulfurs and 2 H2Os. Got to do that too. Now, if I add a bunch of O, what direction is the reaction going to go? It goes away from the stuff I add. So if I add a bunch of a reactant, reaction is going to go forward. And if I go forward, what eventually will happen to the H2O concentration? both products would go up, both reactants would go down. So this is an increase. All right. This actually adds the exact same stuff, right? O2 added. It still cause a go, it would still make the reaction go forward, wouldn't it? So what happens to the H2S concentration? Negative, it's going down. Add oxygen, cause the reaction to go forward. All your products go up in concentration, all the reactants go down. All right, how about removing something? If I remove it to different equation now. Removing H2S, so this goes away. What direction do you think the reaction is going to be stressed towards? Backwards, because you got to replace what you took away. If we're going backwards, both of these go up, both of these go down. So what's going to happen to the O2 concentration? It's going up. Now, it turns out the next one's a trick. Why will adding sulfur do nothing?
Zeros in both.
Hmm?
They'll create zeros in the reactants and in the products.
This is the only sulfur,
Oh,
but why is it not doing a thing? Let's write the Q for it real quick. Why is the Q of this equation only have water on top? Why is that the Q? Remember, the solids don't go into our Qs because the concentration's fixed. Concentration is related to density. Turns out if you add sulfur to this, it won't do anything because you can't change the concentration of sulfur. So what I do to typically catch that stuff is when I go through a problem like this and I look at these, I pretty much immediately, whenever I see a sulfur or a solid, I put a line through it to remind me it will never be in my Q. It's never going to affect Le Chatelier. There's not much I can do to sulfur to mess it up. Now, in the grand scheme of things, that is a bit limited because what is molarity? What is concentration? Moles over liters. The liter is the entire container. Isn't the solid taking up space? So eventually, if you add enough solid, you're going to affect the concentrations of all the other species. But it would need to be drastically changing the volume type of thing. That just adds more complexity to the problem that pops up in later chemistries. But yeah, the solids do technically affect it slightly, but it's not because it changes the concentration of the solid, it just changes the concentration of everything else. Isn't that loads of fun? All right, I just said we don't do anything to solids. Turns out gases will mess with us some. So like on this one, you see how the other three species are gases? And even worse, you see how as reactants, we have 3 molecules that are gas. And as products, there's only 2. Think about this in terms of pressure, like the balloons. As this reaction goes forward, wouldn't the volume of the gases or the pressure of that drop? Because we have fewer gas molecules? Yeah. So this, if I had a mole of this and a mole of that, well, it'd be 2 moles of that. I would have, 60 liters of gas per mole. And over here, I'd only have like 44. So the volume would be able to drop because the number of gas molecules is fewer. Well, we can take advantage of that concept. If I know they're gases, and we're going to keep it simple, I got something with 2 moles of gas and 1 mole of gas. If I want to get it to favor one side or the other, I can change the volume, which changes the pressure. What I mean by that is if I actually lift that up, increase the volume, the pressure will drop and will shift towards the side of the reaction with more moles of gas. On this case, we go backwards. because there's more gas molecules as reactants. So if I increase the volume, decrease the pressure, you shift toward the side with more gas molecules. And what do you think's happening if I decrease the volume? The exact opposite, go to the side with fewer moles of gas. So like that example I had there, since there's more moles of gas as reactants, if I increase the volume, the reaction would go backwards. If I decrease the volume, the reaction would go forwards. Just by changing the volume. So let's look at some examples of that and make sure we get an idea of what we're going to do. All right, so the very first one, and think of this, I want to cause a shift to go forward in all of these because it says we want to make more products. So I want to cause that first one to go forward. And which side has more gases, the reactants or products? Products, because there's no gases on the reactants. The only way I can make that go forward is to increase the volume, and therefore I'd shift towards the side with more gas molecules. So increase volume, shift towards more gas molecules. Is that the same thing on the second one?
No,
And why is it not?
they're both gas and the reactants. And
Yeah, but I also have more gas molecules as reactants. 3 versus 1. So to go forward, we are decreasing the volume because we want to go towards the side with less moles of gas. The last one's kind of tricky. Can I do anything with the volume to make that shift? Or better way, if they ask, better question, does either side have more moles of gas? No, got 2 moles of gas as reactants, 2 moles of gas as products. Volume change will do nothing. I'm gonna do delta volume, does nothing. Sweet, huh? Maybe not sweet. Pretty darn cool though. We have one more thing to do and it's actually with gases, but I'm not doing that in 2 minutes because I don't want to. But got more done than this morning, so not having to write on the wall is a lot faster. That's actually nice. And they will like it if I share this recording with them rather than because I have 4 people online with that class right now. And you gotta imagine that was a pain in the butt for me to have to walk over the screen and try to get the camera to follow me and stay there.
What does your shirt say?
Mine today says SDM Race Jacksonville. And this is 2018. This is the last year I did that one.
Was it an actual race you went to?
A foot race, yeah. Half marathon?
Oh, you did it or you just watched it?
No, I didn't.
Some people, do you know how many people go and just stand there and
Oh,
watch
that's
people
true.
run?
You should do this one. So Jacksonville used to go right by the Maxwell House manufacturing facility. I need to get someone that works there because that's the perfect place for a water stop that has coffee.
I tried one of those 5Ks in high school for like a fundraiser. And I had someone pick me up like halfway through it. I'm not even gonna lie. I didn't even finish it. I couldn't.
I volunteered at one and then people wouldn't even run it, but they'll go collect the medals at the end because they give everybody medals.
I
Yeah.
didn't even think about that. I just left.
I just gotta brag. Mathematics.
Running just isn't fun for me.
It's like till you get a certain distance and it becomes fun.
Yeah, no one ever knows their full potential unless you're in like grave danger or something. And then you can run very fast.
Have a good day, sir.
That's not it. Do I have to, Fanatic is silent, there we go. Do I have to sign in to see this? No, but Fanatic number, that'll work. And no, that's not gonna work. Can we go with year-to-date races? Lifetime races. Is that gonna be an easier search? Maybe. What are you doing here? Fine. Search.
You can look up your records.
There he is.
Nice.
26.
Is the symbols how many you've done?
It's
6?
the number I was able to register on here. So they have criteria, but 107 half marathons
Well, dang.
in 61 months in a row. So 1 a month for 61 months straight.
How many shirts do you have? 107.
I have probably a shirt for every one of those races, plus some. Some of those are tech shirts, which I don't wear to school because they're just ugly and they got turned into a blanket. I have a few, but I think it'll show all of these. But this means the level you're at. So to get the 6 moons up there, I did 4 half marathons in a weekend. So once Friday night, one Saturday morning, one Saturday night, one Sunday morning. Sides of my foot fell off for that.
Yeah, I bet.
Well, my shoes fell apart in the first race. I probably should have stopped running, but it's self-destructive behavior. That's the best way to describe it. Ragnar in December, I fell and fractured my ankle. I didn't know it was fractured, but I didn't run the rest of the race. I'm getting going again, and back in January, I think it was January, they had the Skydive Ultra, and I really wanted to go do it because you jump out of a plane and then run a half marathon. But I figured I probably shouldn't do that with a still fractured ankle. So Saturday, I'm doing the 5K here in town of Valentine's 5K. And my goal is just to run it as much as possible. Hopefully the ankle don't hurt too bad. I haven't made it much more than half mile so far without it irritating me. But yeah, that's I was running a lot more. I don't even think you can actually bring up all the races anymore with how they got it set up right now. But that was all from November, I don't remember, the wine and dine at Disney, 1 a month up until January of 2019. But I could have run February, I just didn't. I had enough, had to take a break from it. Which I kind of regret because 61 months in a row. I don't even know if I remember how to get onto this site anymore to update anything. But these people are weird because they changed their rules during COVID because they can. Folks, have a great day. And come run Saturday. It's fun.
No thanks.